Welcome to the deep dive. Today we're jumping into something really fascinating from abstract mathematics. It's
Yeah.
about combinatorial design, Steiner systems, and this big quest called the design of the century. Sounds impressive, right?
It certainly is. It represents a really deep challenge in arranging things perfectly.
Okay, let's unpack this a bit. Steiner systems, perfect arrangements. What's the basic idea we need to get our heads around, like the core concept?
Sure. Imagine you have a set of points, let's say n points. You want to group them into smaller sets or blocks, all of the same size, say k. Now, the key, the absolute defining property of a Steiner system, is that if you pick any smaller number of points, t points, they appear together in exactly one of those larger k-sized blocks.
Exactly one. So no overlap in coverage for those smaller t-sets.
Precisely. It's about, well, combinatorial perfection, maximum efficiency in how subsets are cut.
Okay, and the notation, ST, KN,
Yeah.
just captures that. T-points must be unique within k-size blocks drawn from n total points.
That's the formal way, yes.
And historically, people often start with S2, 3n, the Steiner triple systems. You mentioned the Fano plane before we started.
Exactly. The Fano plane is a beautiful small example. It's S237, so 7 points, grouped into blocks of 3. And the rule holds, any pair of points you pick, they lie on exactly one of those 3-point lines.
Simple, elegant, but things get way more complicated fast, I imagine.
They do, especially when you move to blocks of 4, so K4. Which brings us, neatly, to the big one, the S2-4-100 system.
Ah, the design of the century. So 100 points, blocks of 4, every pair covered just once. But I heard the existence of S2-4-100 itself wasn't the main puzzle.
Well, finding an S2-4-100 is hard, but yes, the specific challenge, the reason for the nickname, was an additional constraint, a very specific coloring constraint.
Okay, coloring, how does that work?
You had to be able to color all 100 points with just 2 colors, let's say yellow and blue, in such a way that every single block of 4 points was unbalanced. Specifically, each block had to have 3 points of one color and just 1 point of the other color. 3 yellow, 1 blue, or 3 blue, 1 yellow. Never 2 and 2.
Every single block. Out of how many?
Out of all 825 blocks, as it turned out.
Wow. That sounds incredibly restrictive. And you mentioned earlier work showed this was impossible for smaller numbers.
That's right. It had been proven mathematically that this specific kind of unbalanced 3-1 coloring couldn't exist for any S2-4n system where n was between 4 and, well, 99, essentially.
So why even look at 100? If it failed everywhere else, why suspect 100 would suddenly work? Seems like a long shot.
It does, but the underlying math, the number theory conditions needed for these designs to exist, didn't actually rule out N100 for this property. The structural proofs failed below 100, but 100 was like this boundary case. It was tantalizing because it was the first value not explicitly forbidden by those earlier proofs. If it failed at 102, then maybe the property was just impossible, full stop.
Okay, that makes sense. It was the edge case. So how did they finally find it? It wasn't some elegant pen and paper proof, was it?
Oh, definitely not. This was a triumph of computation, really. Confirming this abstract thing existed needed raw power. A team at the Open University, Forbes, Grinnell, and Griggs, they finally nailed it after, I think, the problem had been open for over 25 years.
25 years. And the final push, how much computing did that take?
The reports say the final successful search phase took over 40 weeks of computation time. On personal computers, mind you, but running constantly.
20 weeks. That really drives home the scale and the difficulty.
Yeah.
Just arranging these 100 points with that color rule.
It's staggering. And the final design, as I said, has 825 blocks. But there was another neat discovery within it.
Oh, what was that?
The way the successful coloring worked out, the points of one color, let's say the 45 yellow points, they weren't just randomly scattered. They actually formed their own smaller, perfect Steiner system inside the big one. Specifically, they formed an S2-3-45, a Steiner triple system made of 330 yellow triples nested within the larger S2-400 third. A beautiful hidden structure.
That's pretty amazing. So it wasn't just finding it, but finding the structure within the structure. What should we, the listeners, take away from this deep dive?
I think it shows that these very abstract mathematical objects, these designs, they're not just curiosities. They relate to deep structures in math, like sporadic groups, but also underpin practical things.
Right, things like error-correcting codes that, make our digital world function, or data compression.
Exactly. Coding theory, experimental design, even theoretical physics sometimes touches on these combinatorial structures. Perfect arrangement has real consequences.
It really drives home how exploring these pure abstract limits can lead to unexpected insights and applications. And speaking of smart design and cutting-edge applications, If you're looking into AI for education or integrating it into your business, EmberSilk is the answer. Check them out at embersilk.com. So if this dive into mathematical structure sparked your curiosity, please do subscribe to our channel and maybe leave us a 5-star review. It genuinely helps us bring more deep dives like this to you. Until next time, keep exploring.